Welcome to this webinar dedicated to the pipeline integrity and more specifically to the in-ditch crack assessment using tangential eddy current array. Here's an overview of what we've prepared for you today. We will start with a brief introduction on the target application. We'll then present our solution and our products. You will then watch a video demonstrating the potential of our products and how to acquire and analyze data. And finally, we will wrap up and summarize the webinar before we go to a Q&A session. So as mentioned just before, we're talking about pipeline integrity and more specifically the in-ditch inspection of pipelines. As you may know, the efficiency and safety of pipelines is very important, as failure can seriously impact humans and the environment, and obviously there's some financial concern if it happens. It's therefore critical to find and assess defects such as fatigue cracking and also stress corrosion cracking, as they can limit the safe use of carbon steel pipelines. Pipeline operators closely monitor their assets and they are very familiar with this type of cracks, which is the most prevalent defect in in-service carbon steel secondly after the corrosion. However, assessing cracking on such pipelines can prove very tricky because of the condition linked with the asset, the rough environments, the presence of welds, and the surface condition. Plus, most of the times the surface are covered with several layers of coatings, so it can be a bit difficult. There are different types of welds in pipelines: longitudinal, girth, and spiral weld. Completely assessing those is essential because these joints are prone to cracking at different areas. Can be the weld centerline, the heat affected zone, and also the toe area. Conventional methods such as magnetic particle and liquid penetrant testing are often used. They're effective, but they lack some practicality and they have known drawbacks. For example, the need for surface preparation. You need to remove the coating, clean the surface, and prepare it. Obviously, if you remove the coating, you have to reinstall it, which takes time. You only have crude information and manual length sizing of the cracked area. And you're lacking digital data, so you can't archive the information properly. And also, everything has to be done on site. There's no post-analysis possible. So TECA is the best alternative to this in most situations, as it provides a complete map of the weld area in one single pass, without the need for preparation of the surface before. This with the added value of having some information about both length and depth of crack, which we'll demonstrate later. Stress corrosion cracking is an environmentally assisted type of cracking located on the external surface of carbon steel pipeline, because sometimes corrosive soil can come in contact with the surface of the pipeline. SCC, if not identified and managed properly, they can expand, they can coalesce, and then form long and deep cracks, which can lead to failure if we don't do anything about. Again, in this case, conventional methods like magnetic particle is used, but that takes a lot of time. It's sensitive to weather condition and rely heavily on the user skills. For example, here we are showing you some imaging showing condensation on the surface of a gas pipeline, which is maintained at a low temperature, which make the magnetic particle testing very complicated, if not impossible. With the TECA and the Sharck high-resolution probe, detecting SCC in those conditions in one single pass, it's not a problem. You don't have to prepare anything, and the result results in shorter excavation, inspection, and repair time, and hence to lower costs. We conducted some on-site inspection with some of our customers. These are some examples of data we collected. You can easily see that the cracking is highlighted on the C-scan very easily, which provide the map of the inspected inner area, similar to magnetic particle information. And using the cursor on the software, it's possible to rapidly analyze the data and get a full assessment of the defect. Again, using the strip shot at the bottom of the screen, you can clearly see the depth profile of your cracking and spot the deepest position and measure it very easily. Here is a straight comparison of data collected with both TECA and magnetic particle testing. The map you can see here is very similar to magnetic testing, which is the added value that we could measure the depth of the different area cracked around it. So it's a perfect match. For the product presentation, the instrument and the probes that we have offer a complete solution for pipeline integrity. They are specifically designed for field use and are very fast and easy to use for crack assessment. And the software is embedded in the instrument, so you don't need a computer linked to the instrument. You can just plug the probe to the instrument and do your inspection. So the Reddy is, as I say, a portable solution. It's very light. It's been designed for field application, so it's rugged and sealed. The IP rating is 65, so no problem with weather condition. And it has a large touchscreen that you can use for analyzing your data as well directly on the instrument. The Sharck probe were designed with care because we wanted the ergonomic to be as easy as possible and to enable a secure handling during scanning and to use in field condition. So first of all, the butt weld Sharck probe is designed for weld inspection, and it has control buttons on the top, so you can do all of the control from the probe directly. You don't have to go back to the instrument. You can stop the acquisition, balance the probe, and save the data very easily. We added also some marks on the top casing, so you can position the probe very easily because you know where the active area of the probe is. Also, this probe has individual spring-loaded elements that helps to conform to the weld crown, so you don't have to prepare the weld at all. You can just inspect it as welded. For the Sharck high-resolution probe, this one is designed for the bare material inspection. So it has a semi-flexible active area with a quick curvature adjustment, which enables the user to adapt the active area to the pipe curvature under inspection. Also, it has 4 guiding wheels that helps to keep the probe stability during the scanning. As for the data display, we tailored the setup and we developed dedicated analysis tools so that everything you need to sentence your weld is visible on the screen using the default layout. No need to adjust the frequency or the gain the way you would do with the other type of control using eddy current array. This one is a plug-and-play solution. You connect your probe to your instrument and you're ready to do your inspection. Once the data are collected, you can straight away do the analysis. All you need to do is to look for crack-like indication using the 2C scans. Move your cursor to the area where the crack is, and then you'll see that the data information is clearly appearing on the information info field on the right-hand side of the screen. So you have the depth, the length, and also some information about the liftoff. The strip chart at the bottom is dedicated to transverse cracking. So in one single path, you can detect actual and transverse crack, and everything is displayed there. And then more advanced user can also make use of the impedance plane. This display is slightly different from the previous one. This one is a display of the data collected with the Sharck high-resolution probe. Basically, you just need one C-scan for this one to spot a crack-like indication, and the strip chart includes a side view of your C-scan. It's kind of a similar view to the B-scan you get with phased array ultrasonic testing. It shows the response of one of the probe elements, and you can use the cursor to easily get a measurement as well. This view enables you to quickly assess the cracking profile and to spot the deepest area. For example, here we have a long notch that was made with a stepped profile at 1, 2, and 3 millimeter deep. And you can see the different steps very easily and clearly. And moving the cursor to one or the other, you'll get a straight measurement of the depth, and it's clearly displayed on the right-hand side. Michael Sirois will go into this in more details very shortly in the demonstration video. Finally, this is an example of a custom display you can quickly create, so you can tailor it to your needs. Here you can see the side view display is a bit different from the previous slide. Basically, instead of showing just one element of the probe, we are showing all of them. So in this view, it's very useful when you have a dense colony of stress corrosion cracking, because you can locate the deepest point in the full scanned area. Okay, at this point in this webinar, I'd like to play you a video we recorded a few days ago with Michael Sirois, our Surface Technology Director. While you watch, I'll be interacting with you through questions that will pop up on your screen. Send us some questions during Mike's demo, and I will answer them during the Q&A session.
Hi everybody, thank you for being here today for this webinar about the TECA technology for the pipeline inspection. My name is Michael Sirois and I'm a Technical Director for Surface Application with Eddyfi. So basically today I'm gonna demo two of our Sharck probe with the portable instrument here, the Reddy instrument. Basically the two probes that I want to demo will be these probes. First probe is the Sharck probe, basically for a butt weld inspection. So this probe has a spring-loaded element, so that makes that the probe can fit to any kind of butt weld. So if we talk about pipelines, so this probe could inspect the girth weld, the longitudinal weld, and even the spiral weld. And we could run with this same probe both circumferential or longitudinal scan along the pipe. And the other probe that I'm going to demo a little bit later will be the high-resolution version of this butt weld. But this mechanical design mainly help to inspect the pipe surface, not the weld. So we have a flexible shoe here which can fit to the pipe diameter to be inspected. And based on this design, this probe will carry only longitudinal scan along the pipe. So if we get back to this first Sharck probe to begin, in fact, as I explained, this is going to be for basically for butt weld inspection. There is an encoder already integrated in the probe. So this encoder will help for the defect positioning and for the length the sizing. And we have also some button on the probe to control the acquisition, the balance, and even the calibration. And basically this probe has a 2-inch coverage. So during a single scan, we're going to cover the eyes, the toes, and the crown only in one pass. So basically here, I've already loaded the setup file on the Reddy, and the probe has been already calibrated just to speed up. I just don't want to go too deep in the detail about how to use the probe. But so the sample that we're going to use for the demo here is a Flowtech plate with a butt weld in it. So basically there is some fatigue crack which has been induced along the weld, and we're going to try to detect all these cracks with this butt weld here. Just few details about the first probe that we're going to use. So this probe is able to deal with up to 3 mm of lift-off or coating. So no need to remove the coating before the inspection. And regarding the probe capability in terms of detection and depth sizing, so this probe is going to detect the defect or the crack in all orientation, both axial and transverse. And regarding the depth sizing, we're going to be able to size with this probe defect as deep as 7 mm in depth with a pretty good accuracy between ±10–15%. So considering the fact that we have to manage the weld roughness, we have to manage the material properties and many other parameters. So on carbon steel like that, this is a pretty high level of accuracy. So here we go. I'm gonna just now show you how to use this probe. So the first step basically is simply to balance the probe in the air like that. So I'm using the button on the top of the probe cover to balance the probe. And after that, I'm ready to scan the weld. I'm gonna hit the start button and align the probe right at the center of the weld. And here we go. I've scanned already the entire plate. And if we look at the Reddy screen now, I'm going to just explain quickly the main view that we see on this instrument. So the most powerful and useful view for me are definitively the C-scan view. So we have two C-scan. The first one, the top here at the left, is what we call the depth C-scan. And just underneath, we have another C-scan, which is the length C-scan. Each C-scan is composed of 22 channels because the probe itself has 22 channels. So we have 22 receivers capable of measuring the depth of the crack during the scan. And in each element, we have also another receiver which is able to detect the length of the defect. So this is basically why we are using two C-scan, one for the depth monitoring and the other one for the length sizing. So if I scroll up and down the cursor on the C-scan, I'm going to just switch from one channel to the next one. So we can see here in the Lissajou view the number of the channel on which the cursor is located. So we have these two C-scan here, and just beside here we have the Lissajou view for the depth C-scan. So basically the analysis or the depth sizing is going to be done from that view. So we are doing the analysis directly from the raw channel. And just below we have the length Lissajou. And if we go down furthermore, we have 3 info fields. And this info field provides us the information about the depth of the indication that we detected, the length, and if there was some liftoff, we will also display the liftoff. And finally here, right at the bottom, we have a strip chart. And this strip chart, in fact, contains the transverse channel. So basically on the Reddy interface, we didn't have enough space to put 3 C-scans side by side. So we prefer for the transverse channel just to display a side view like that. So if we add a transverse indication, whichever on which channel we're going to detect it, we're going to just see this channel. And if we want to push the analysis much further, we can switch to the transverse C-scan here to analyze the transverse indication. Basically, we try to design the user interface to make the use of this instrument and software as user-friendly as possible. So basically, for beginners, it's pretty easy to locate the indication on the depth C-scan. In fact, we are looking for the yellow-red indication. So the background by default is set to green. We can see the color palette here. So when we have an indication which appeared yellow, orange, green, that not green but red, that means that we have an indication here. And we just need to move the cursor close to this indication. And in the software, there is an algorithm which has been developed to help the data analysis. In fact, just by hitting this little button here, the software is going to move the cursor on the channel which has detected the deepest measurement. And by default here, we're going to have the depth of this indication. So in that case, the depth was set to 4.2 millimeter. And regarding the length, this is an automatic measurement once again. This time, the measurement has been recorded from the length channel. So as soon as we detect an indication on the depth channel, if it's a crack on the length channel, exactly on the length C-scan, exactly at the same position, we're going to got a blue and a red spot like this. So the blue spot gives us the information about the first end of the crack, and the red spot is the end of this same crack, and we just need to measure the distance between the beginning, the blue spot, and the red spot. And as we are encoded, we have directly the length of the indication. And another thing which is pretty interesting here is that with that particular probe and the TECA technology, we have the capability to monitor the liftoff dynamically during the scan. So that means that if we have some liftoff somewhere along the scan, the software is able to monitor the liftoff and to compensate dynamically the signal for that liftoff. Because as some of you knows, when we have liftoff, we're going to lose some amplitude on the signal, and the depth sizing might be wrong. So this is why we developed this tool in the software to compensate for the liftoff. As I press this button here, in fact, the software, as I explained, will move the cursor on the channel with the highest or the deepest measurement. And by default, it's going to propose you a baseline here in the Lissajous view. So if you want to adjust or fine-tune the position of the baseline, a power user could do it pretty easily. And after that, we also add in this Lissajous view here some curve, depth curve. So basically, once we define the baseline, depending about the amplitude of the defect, we're gonna reach a different depth line, which are all identified here in the Lissajous view. So that makes the analysis even more simpler. Last thing which is pretty interesting with TECA is the capability of the software to compensate as well for the permeability, because all along the weld, if for some reason the permeability changed, that could definitively have an impact on the depth sizing. So for this, when we spot another indication like this on our data, we just hit this button like that to ask for the deepest measurement, and we're going to just hit the system calibration windows here and do a user mat like this. So when I do this user mat calibration like that, so the software is going to use some data point around the defect that we detected, will evaluate the permeability locally there, and it's going to apply also a compensation for the permeability. So that's a pretty interesting tool for to get a better accuracy on the depth sizing. So I think it's pretty it for the Sharck probe. The next probe that I'm going to demo will be the high resolution Sharck probe. And as I said before, this one is more for the pipeline body inspection, not for the weld. And with this probe here, we have some elements inside the probe, or coil, which are about half the size of the Sharck butt weld. So that means that we're going to have a higher sensitivity, a better resolution, but in revenge, we're going to penetrate a little bit less in the material, and we're going to tolerate less liftoff as well. So in terms of penetration, we're going to go down to 3 millimeter. And regarding the liftoff that we can manage with this probe, we're going to go at maybe 1.5, 2 millimeter. Okay, so I'm going to just change the probe for the SCC. So the high resolution Sharck probe has been mainly designed for the SCC, stress corrosion cracking detection and depth sizing on pipeline. So here we go. So the first connector is basically for the probe itself, and we have the encoder connector here to get the encoder connected to the instrument. I'm gonna just load the right setup file here. So few details quickly about this design. So basically, once again, there is an encoder integrated in the probe body. So these two wheels here are attached together. So, and the encoder is linked to these wheels. Basically, we have also a spring-loaded shoe like that, in a way to keep a constant pressure under the probe during the scan. And also, this shoe can be bent to fit to the pipe diameter. Now we have the setup file loaded, I think. We have pretty much the same view, but I'm going to go more in detail about the view for this probe here. Same thing here for the to use this probe. Basically, we're going to balance the probe in the air. And also, I forgot to do it, but we're going to just, actually the probe is set flat. I'm going to just adjust the shoe of the probe to the curvature of the pipe. So as you can see now, the shoe is curved to this pipe diameter. And after that, I'm ready to go. So I'm going to use the touchscreen of the instrument now, scanning the defect like this. And here we go, stop the acquisition. With this high resolution version of the Sharck probe, we have a smaller element, as I explained before, and we have 3 rows of coil to get a higher resolution. The coverage of this probe is about 75 millimeter, so a bit wider than what we got with the Sharck probe. And this is the scan, the data that we got during the scan. So I'm going to just zoom out on the defect. First thing that we can do here is to, as I explained before, to do a user math to just adjust the permeability, to make in fact a permeability compensation for this alloy here. Same way to do it, calibration tab, system. I'm going to select user math, and here we go. The material is now well compensated for the liftoff. On this plate here, this is a X52 sample, and we added some EDM notches in it with various parameters in a way to simulate some feature that we could meet on real SCC. So in fact, one of these defects has a bottom with different depth at 1, 2, and 3 millimeter. So as I'm going to show you, we're going to be able to detect size and also track the profile of these cracks. And we added also some very short crack to show the sensitivity, high sensitivity of the probe, and also some crack side by side to evaluate the transverse and the axial resolution of the probe. So the first interesting result that I want to show here is this defect here at the bottom of the C-scan, where we add a different step at the bottom. So we can clearly here track the profile of this defect. So the first plateau here is at 1 millimeter. So a little bit farther away we were at 2 millimeter, and here at 3 millimeter. So when we have a high density colony of SCC, this view here is pretty useful. And if we have a look at this Lissajous view here, it's pretty easy to evaluate the depth of each section. So if I move the cursor here on the first section of this defect, I can see the red circle here is there to identify where the cursor is located, so in the 1 millimeter depth area. And we can see that the defect just reached the 1 millimeter curve. If we move the cursor a little bit farther away, and I adjust a bit the baseline, we are almost at 2 millimeter. And here finally, we were over, if I move the baseline at the right place, we were over the next line, so pretty much close to 3 millimeter. We have also the same capability here in terms of locating the channel with the deepest measurement. So once again, we're going to use the same button like this, and automatically the software is going to move the cursor on the channel with the deepest measurement. So in that case here, we added two defects very close, one from each other. I think that the distance between these defects was about 3 millimeters. If we look at the strip chart below, we can see that the operating point just moved up because we were on the first defect, and we reached back the null mark here before detecting the other defect. So that means that in terms of axial resolution, we could distinguish defect which could be closer than this one. If we were looking for transverse resolution here, there is two defects side by side, and they are distanced by 3 millimeters also circumferentially. So in that case, we can see that we are barely at the limit of the transverse resolution for this probe. And the last thing here, this little defect here is a 3 millimeter long indication, and it's 1 millimeter deep. So we can see here that on the depth sizing, we were pretty much on it also. Still have a few minutes, so I'm going to scan a real SCC sample colony with the SCC colony in it. So we're going to just show you which kind of result we're going to get with the Sharck HR probe on a real colony. So I'm going to just start the acquisition. Stop. So here we go. So basically, if I'm going to just play with my color palette because the defects here are not so deep in this colony. There we go. Okay. So here, if we would compare the MPI which has been done on it to this C-scan view like that, we could almost find or discriminate every single crack one by one. And basically, the defect which appear in dark red are the area where we had the deepest measurement. So just I'm going to just analyze it pretty quickly, a quick user math like this. So here we go. The C-scan is a little bit more clear. I'm going to just close the cursor, zoom on this area here, and I'm going to ask the software to find out the deepest measurement. And here we go. So basically, the deepest measurement has been recorded here. We have something at about 1.2 millimeter. If I want to adjust my baseline, so I could do it easily like that. So that means that this indication was about 1.4 millimeter deep. And on this side view here, on this particular channel, we can also track the progression of the profile on this same crack. So this is pretty much it for the demo with the Sharck probe. So hopefully you've enjoyed it. Thank you for watching. See you next time.
I hope you find the demonstration useful and that you were able to assess how the TECA technology and our products can play an important role in your pipeline integrity. And some key points to remember is that this solution is currently successfully used on site by some of our customers. It's one of the fastest on the solution on the market. It's very easy to set up with minimum preparation requirements. A simple step calibration is needed at the beginning, but it takes a few seconds. It's very repeatable, so a given area scanned by different people or the same area scanned by the same person many times will always get you the same results. And it's a one-man operation using the Reddy. So it's just the Reddy, the probe, and that's all you need to do your inspection. The Sharck probe with the Reddy portable instrument is the powered solution for direct assessment of carbon steel pipeline. So you can use it in service. It's not affected by weather condition, no condensation, no rain, for example. It doesn't matter if you have any. As I said before, no surface preparation necessary, so you don't need to remove the coating as long as it's not conductive and within the limits of the solution. So 3 millimeter for the Sharck butt weld and 2 millimeter for the Sharck high resolution probe. It can detect and size surface breaking cracks in one single pass and see interlinking cracks too. It's very user-friendly with a dedicated interface and a data analysis assistant tool. So you can rapidly spot and measure the deepest point in a SCC colony, for example, using the different views. It's an extremely intuitive solution. Thanks to the software, it's easy to navigate and you can customize your display and suit it to your needs. And it complies as well with the NACE standard practice SP0204. Okay, so as for the probe, just to wrap up the capabilities, is that the butt weld Sharck probe can detect both actual and transverse crack in one single pass, and it can conform to the weld crown too. You can detect, you can size crack up to 7 millimeter deep. Any crack deeper than that can be detected, but we won't give a sizing information. And again, the lift-off, we have a dynamic lift-off compensation live while you do the scanning, so we can cope up to 3 millimeter of lift-off. The Sharck high resolution probe has a better resolution, uses smaller elements than the butt weld probe, so it's a lot more sensitive to short and shallow defects, like SCC, for example. So in this case, we can always only look for actual cracking in the scan direction, but we can conform the surface, the active surface of the probe for pipe from 10 inches up to flat. And the sizing capability is up to 3 millimeter deep for this probe, and they can cope with 2 millimeter of liftoff. The same compensation applies for both probes. All right, so that's a wrap up for today's live webinar. We're ready for some questions. You send us some of them during the demonstration video. So I'll tackle this first, but you still have time to send more if you want to. Okay, so the first one is, do I have to calibrate and how do I do it? Yes, we didn't show it during the demonstration because it's a simple step and there's a calibration wizard within the software to help you doing it. But basically, we take three reference points: the air, the aluminium, and the carbon steel under inspection. And it's a very quick process. You just need to move the probe from one material to the other. It just takes 5 to 10 seconds to do it. And basically what it does is just adjusting gain and rotation, so we get the right sizing accuracy for during the inspection and the analysis. The second one, can I generate a report from the instrument? Yes, that's a good question. Anytime you're going to find a defect during the analysis, you can call it using the cursor and the indication button on the unit, and that will create an entry into the report. And each entry has a number of information that you can tailor to your needs. So you can get like the depth measurement, the length measurement, the position, the start stop, which element find the information. And then you can generate a full report out of those indications through the software. And it can be at different formats, so PDF, Word or Excel. And you can also get an image of the C-scan you use for the analysis. The other one is which coating can I use the Sharck on? So any kind of coating, as long as it's not conductive. So it needs to be seen as just a lift-off, basically. Again, it's 3 millimeter for the butt weld Sharck probe and 2 millimeter for the high resolution one. The other question is on which diameter can I use the Sharck probe? You can use both Sharck probes for pipe outer diameter from 10 inches, so 254 millimeter, when you do an actual scanning. The butt weld, you can also do circumferential scanning, and it's about the same diameter. The Sharck high-resolution probe is not designed to scan circumferentially around the pipe. Next question is, what are the actual and circumferential resolution of the Sharck high-resolution probe? As Michael demonstrated, we can easily discriminate notches and cracks that are 1 to 2 millimeter apart in the actual direction. And I'd say that for the circumferential resolution, it's about 3 millimeter. I have another question on the sizing accuracy, the depth sizing accuracy. So for the butt weld, we said that we can size up to 7 millimeter deep in both the weld, the HSZ, and the toes. And the accuracy for that is plus or minus 10 to 15%. It really depends how rough it is, the weld. So you can, depends on the condition, there's a slight variation there. But because we compensate for permeability and lift-off, it's what we can achieve. For the Sharck high-resolution probe, it has a higher sensitivity and a bigger resolution than the other probe because it has smaller elements. So this one can only size up to 3 millimeter deep. And I'd say that the accuracy is about plus or minus 10% on an isolated crack. So if the SCC colony is very dense, this accuracy will be a bit affected. Okay, I have time for the one last question. This one is on the impact of liftoff on the signal and the measurement. So liftoff has a great impact on eddy current signals. And hence it can have an impact on the depth sizing. That's why we have a dynamic liftoff process and compensation. So basically, every time a point is data measurement is taken, we measure the liftoff and compensate for it. So basically, through this compensation, a given defect will always have the same amplitude, whatever the liftoff we will see it with. So there's no great impact as long as we stay within the range that we specified before. Okay, so I think that's all the time we had for today. We will answer the question we did not get around offline later on by emails. I'd like to thank you for attending this live webinar, and I hope you enjoyed it. And then until next time, have a great day. Thank you.